Today we're going to be talking about reactions with carbonyls using carbon, nitrogen, and oxygen nucleophiles. So up here on the screen, these are just a few of the nucleophiles we're going to be looking at. So as you can see, each atom has a few listed nucleophiles. I'm not going to go through reactions with all of these individually, but I will be going through reactions for each category, which you can then apply to these other nucleophiles that are within the same category. I do have hydrogen listed as well, which is going to usually be pulled from an acid, so that will pop up in our reactions, but it's not going to be a distinct reaction that we'll go over by itself. First up, we're going to go over reactions between carbon nucleophiles and carbonyls. The product formed with these types of reactions will be an ylide. Here I have it spelled with an E at the end, but you'll also see it without the E. It's the exact same thing. So within our ylide class of molecules, there are those that are stabilized and those that are unstabilized. Ylides with a resonance form are considered stabilized, just as a lot of molecules are more stabilized with a resonance form. You're typically going to see that with ylides containing a carbonyl, that there's going to be a resonance structure, and that's because that CO bond can be manipulated. Ylides without a resonance form are considered unstabilized. For stabilized ylides, you'll find E alkenes, and for those that are unstabilized, they'll be Z alkenes. Let's go over the mechanism for forming a stabilized ylide from a carbon nucleophile. Our starting material here is going to be triphenylphosphine, which is an electrophile, as you can see by that lone pair on it, and then we're also going to use a Grignard reagent. First, we're going to break the bond between the halide and the alkyl group. Then a nucleophilic attack will occur. Next, we're going to use that lithium reagent that is right here. That lithium reagent is going to come in and substitute for the alkyl group that attacked the phosphate earlier. So our ending product is going to be triphenylphosphine with a longer alkyl group from that lithium reagent. This product is resonance stabilized because you can move the electrons around from that PC double bond. Next up, we have reactions with nitrogen nucleophiles. The nitrogen nucleophile is going to be an amine, which can be seen on the right. So it'll depend on how many of these R groups we have on it. So 1 R is going to be primary, 2 is going to be secondary, as seen here, and 3 is going to be tertiary. The products of these reactions are imines and enamines. An imine is a nitrogen double bond. It is when a nitrogen is double bound to a carbon and a single oxygen or single hydrogen right here. In comparison, we have our enamine, which has the 2 hydrogens attached to that nitrogen, but still a nitrogen-carbon double bond. To form imines, we need a carbonyl with a primary amine. First, we are going to push electrons from our carbonyl bond right here over to this oxygen right there. That will allow for a nucleophilic attack by this nucleophile right here at that carbon center. From there, we're going to have a proton transfer where a proton and the amine can transfer over to the oxygen to form an alcohol. Then we're going to take a proton from the molecule of acid and protonate the alcohol to form water. As we know, water is a good leaving group, so it's going to come off the carbon. And to balance things out, nitrogen is going to give some of its electrons, and that is going to allow for a double bond formation that we'll see right here. And then finally, we're going to have deprotonation of the nitrogen, which will allow for regeneration of our acid catalyst. Our end product is going to be an imine. Our other product that we're going to see with these nitrogen nucleophiles is going to be an enamine, which will form from a secondary amine and a carbonyl. This mechanism is a little simpler. It starts with electrons being pushed towards oxygen to break a double bond between carbon and oxygen. So just the contrast with this one is that we're not protonating anything first. We're just immediately breaking that carbon-oxygen bond, or one of them. That single hydrogen, this movement of electrons will allow then for a nucleophilic attack by our nitrogen nucleophile, and the single hydrogen that was on the secondary amine will be used in a proton transfer to oxygen, which will allow for the formation of an alcohol. From there, a hydrogen on a more distant carbon, which is going to be right about here. We're going to see that right there. A hydrogen on a more distant carbon will be used to form a double bond. A shift will occur so nitrogen doesn't have 4 bonds and the final product will be formed, which is an enamine. So as you can see, we have our nitrogen here, and that is going to be the base of our enamine. Next, we have our oxygen nucleophiles, which can form a few different types of products. A hydrate can form, which is when we have 2 alcohol substituents on a single carbon. From there, we can also form a hemiacetal, which is like a hydrate but with an R group on one of the oxygens instead of a hydrogen. Then the hemiacetal can be used to form an acetal, which is when a single carbon has 2 OR substituents on it, so with that carbon between them. Our cyclic acetal is the same thing, but instead of a free OR substituent, if you will, they connect to form a ring. So it's just like this, but instead our R groups are essentially coming here and here. That's the only difference, and that's what you're going to be seeing right here. Let's look at the mechanism for hydrate formation first. We have 2 ways of doing this, acid and base catalyzed. So let's start out with a generic carbonyl right here, which is a ketone. The carbonyl oxygen is going to get protonated first. So this guy right here is going to get protonated first to form an activated carbonyl. This is going to be more reactive, and so it's important in a first step to do this when we're working in an acidic medium. So from here, we're going to break one of those carbon-oxygen bonds, so we're breaking that double bond, and this will allow for water to come in as our nucleophile and attack at that carbon center. Right here, right here we have that water that has come in and attacked. So again, from that H2O addition, now what we're going to do is use another molecule of water to deprotonate right here so that we end up forming our alcohol group of interest, but also the important part is that we are regenerating that acid that we use, so that H3O right here is going to be regenerated, but ultimately this mechanism leads to the formation of a hydrate, and so we have 2 alcohol groups on the same carbon. We can do the same thing with bases, except that it's even simpler. We don't have to protonate the carbonyl alcohol here. All we the carbonyl oxygen here doesn't have to be protonated. All we have to do is break the double bond and give those electrons to the oxygen, so it'll become negative. At the same time, an OH will come and attack from our base, so that is kind of the movement of electrons and then subsequent nucleophilic attack. This leaves us with 1 alcohol group that is formed and a negatively charged oxygen substituent. From here, we can just use water to protonate the oxygen, which allows for the regeneration of our base. So if we're working in acid or base, it's important that we're taking steps to also regenerate what we were previously working with here. So as you can see, we have our hydrate just as we did with forming it in an acid. Now we'll go to hemiacetal formation in an acid background. We're first going to do this by activating the carbonyl, and again that comes from protonating the oxygen, so we're going to use the H, the proton, from our acid to protonate the oxygen. This will then lead to the formation of an activated carbonyl, and through resonance structures we end up creating a carbocation at that carbon center, which can then undergo nucleophilic attack, and in this case we're using ROH as a general form of an oxygen nucleophile. So that oxygen is going to directly attack that carbocation, and it will then, after the attack, be deprotonated, which we'll see right back here, to reform our acid that was used in the reaction. Our product now has both a single OH group and a single OR group. Next we go to acetal formation. I do have a mistake in the title. It is supposed to say acetal formation from hemiacetals, so I apologize. But first we're going to actually start off where we left off. So Assume all the same steps were taken in the last slide to form our hemiacetal starting material. This is kind of a two-step here, so I didn't show the first step because we just did it, but essentially we have to make the hemiacetal before we make the acetal. So first, the alcohol of our hemiacetal will be protonated by the acid to form water. And again, we know that water is a good leaving group, so it will leave the molecule, and we form a carbocation with resonance structure. This carbocation will undergo nucleophilic attack, so an alcohol with an R group can be added. Because they are usually, this part here where we're having a nucleophilic attack of an oxygen nucleophile, we're usually looking at protic solvents here, so those with kind of that OH group on the end. We will have to, once it has been added, so it's been added right here, we're going to have to deprotonate the oxygen in order to get an OR group instead of an ORH group. So we're going to regenerate that acid catalyst and use this guy right here to pick up a proton, which will end up forming our acetal and our acid. So we have those two products. Just to kind of highlight what we're looking at here, this right here is an R group that I have circled here. Then we go to our oxygen, carbon, oxygen, and then everything past that is an R group. We're not going to circle it because then that would mean circling the whole molecule. So as you can see right here, we have an oxygen, carbon, oxygen, and then on each side of those oxygens we have our R groups. Lastly, we'll take a look at cyclic hemiacetal formation. This will come from a carbonyl. In this case, we're using hydroxyaldehyde. So this isn't necessarily like a scary molecule or anything. It is the same thing as a normal aldehyde, but we have a hydroxy on the terminal end, on the other terminal end of the molecule of where that carbonyl is. So due to the hydroxy structure, this can actually fold around to kind of what looks like an open ring structure. Not officially a ring yet, but eventually it will become a closed ring with this synthesis reaction. So first what we got to do, kind of like what we've been doing, is protonate the carbonyl oxygen to form an activated carbonyl. Again, it's just more reactive, that's why we do this. From there, what we do is we break off one of the bonds between carbon and the oxygen of the carbonyl to form a cation that will quickly be attacked by the terminal hydroxy. So on that other side of the molecule, as you can see right here, it's just going to attack that carbon. So it undergoes nucleophilic attack, which makes it so the ring closes. So that at the top there we have our our hydroxy and our hydrogen groups, a ring, and then in that ring we see an embedded oxygen. The only thing we have left to do is to protonate that oxygen that's within the ring, and we're going to do that with, and when we do that, we end up reforming our acid. So what we have here is a cyclic hemiacetal, and again, hemiacetal because we have that hydroxy. With this, we come around, that is our hemiacetal right there, and the acid is regenerated. So that is it for this review. Hopefully this helps.